Hello, by the way. I am Rebecca. I am with the STEM stores at UNO, and I am here to do your event with you tonight. Um, I have several activities set up, and hopefully you will have your materials with you. If not, they're all very easy household materials that you should have access to. So hopefully everything works out with that. So what we're going to start with is our bridges, our folded paper bridges. So you're going to need books, very large books, because if you need a bridge, you need a space to go across if you're going to be making a bridge in the first place. So I find my books, I make sure that they're about even, so that it's an even level that I'm trying to build my bridge across. And then I'm going to take my ruler and I'm going to put them a certain amount of space apart because we are going to fold paper lengthwise, if that makes sense. We're going to fold it this way and make bridges. So this is our folded paper bridge experiment. And I'm going to put my books about an even space away from each other. I want them about 9 inches apart. You can use a ruler to check, or you can just figure out where the paper is going to work when it's spread across, where you have a little overlap on either end. And again, I'm going to bring my computer as far back as it will go and try and adjust it so you can see both me and what I'm doing. And so this is how paper works when it's not folded. It just kind of flops. So we want to build a sturdier bridge out of paper. So what we're going to do is we're going to fold this paper in ways where it will support more weight. And the way we're going to test this weight is with coins. So we're going to take pennies or nickels or dimes and see how many it can support. You can already see my bridge is buckling a little, but we want this bridge to see how much weight this bridge takes before it hits the ground in this case being my dining room table. So we take a couple of pennies, we count how many pennies it takes, and it takes 1 penny for that bridge to collapse. So now I'm going to fold this page again to make it even stronger. And this one isn't buckling at all yet, so we'll see how many pennies it takes. 1, if it'll even stay on it. 1, 2, 3. So that was more than twice the weight that folded in half it would take. So we're going to try some different types of folding for these bridges to see what works best. So one that I like to do is an accordion fold. So how you do an accordion fold, if you've not done one before, is you take about 1 inch of paper and you fold it down. So I did that. I took 1 inch of paper and I folded it down. And you're going to fold it the other way now. So you see I folded this way before, and now I'm folding it down this way. And you're just going to keep doing that accordion fold. You might be saying, Rebecca, why are you doing an accordion folded bridge when everyone knows people can't walk on that and cars can't drive on that? And that is true. It would be very hard for people to walk on or cars to drive on a bridge like this. That would be very hard if you had concrete in ridges like this. It would be really hard to drive on or really hard to walk on. But the thing is that we're doing some experimentation here. We're seeing what works best to solve a problem. And the problem is, how do we get from one side to the other? So we might try some different ways of doing this. And engineers do this all the time. They find problems and they try to make solutions to those problems. And those solutions might seem kind of silly at first, but they can usually be used. What we learn from those experiments can usually be used in a way that is helpful in the future. So even though this ridged bridge might not allow anyone to easily walk across without spraining their ankles, we can learn from the way the design works how to build better bridges. So I have about 50 pennies in this bag, and I've almost run through them already. So we can see that this could a lot better to buckle now. It worked a lot better than our original bridge, which folded twice did. Now I'm pulling out some different coins because I've run out of pennies. We're going to see how much longer this holds up. So that's about 50 pennies, and now I'm adding some nickels. I want to see how many this will support. It just keeps going. And if you're starting to get bored watching me at home, you can try different ways of folding the bridge lengthwise. And there it fell now. So I'm going to move all of this off, and we're going to try a different design. So I wanted to do a bridge the way that highways are shaped. A bridge that is shaped the way highways are. And you might have observed that highways are shaped something like this. There's a flat bottom and then there's two edges pointing upward. And I wanted to see if that is a strong design, because we saw that that corrugated bridge was quite a strong design. It was much stronger than just folding the paper so that there were lots of layers. One of the reasons that that corrugated accordion fold design is so strong is because it makes triangles. Triangles are a great material, a great shape to incorporate in design because they're a very strong shape. So I apologize for any noise. My little sister is home from school, and she is having a great time in the living room, so right next door to me. So now we're going to see if this bridge that I just folded like this is a strong bridge. I want to make sure that it's evenly spaced over both edges, so that's why I'm moving the paper. We'll see how many pennies I can stack into here. Not as many. So this leads me to a question. Would stronger sides help this bridge, or would a stronger base help this bridge? So let's try it with a stronger base first. So I'm going to take another piece of paper and just basically put it underneath and just fold it the same way, with the sides matching up evenly to this bridge construction I already have. I'm going to match it as evenly as possible. And this will make my bridge stronger without making the sides that much stronger. So let's see if that makes that stronger. We got a couple of pennies in before it collapsed. I want to say like 7 or 10. And if we were really doing this like real engineers, we would be very careful to document exactly how much weight goes into something and how much weight something can carry, because that is important to engineers. They build things like houses and stairs and rooms, and they want to know if that's safe for people to use. So they have very accurate weight estimates for how much things can hold, and they have very accurate estimates for what things are safe. But this is just a little experiment to see what different designs work better. So that's 3 pennies, 4 pennies, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Already seeing this bridge buckle just a little bit. About 20. Oh, there it goes. So that was about 20 or 30 pennies. Now I want to see if if strengthening the sides of my bridge would make it stronger instead. And if you're wondering where all of this paper is going to go, I'm going to either use it in an art project, or I'm going to recycle it and make sure that I am making good use of all of the paper that I am using today, because we are using a lot of paper and I don't want it to get wasted. So now what I'm going to do is I'm going to fold the sides over twice so that there are 2 layers of paper on the side. So that's what that's going to look like right there. And I'm going to do the same thing on the other side so that the side is reinforced. And I'm going to see if that works better than reinforcing the bottom of my bridge, because that's an interesting experiment. Right. So there we have 10 pennies already. And now we have 15 pennies. And now we have 20, if it will hold 20. Yep, that'll hold 20. It'll hold 25. Let's see. So there, it's already holding more than our last bridge held. So it seems to be true that the sides are reinforcing the bridge more than the stronger bottom ones. I might wonder why that is. If you think about it, we already found that the layers of paper didn't add as much support as some different folds did. So that is a possibility that those different folds we added strengthened the bridge more. There we go. So I used up all of my, almost all of my 50 pennies and then some of my nickels on that. So we've seen that the stronger bottom doesn't work better than the stronger sides for this highway type bridge design that we used. And we saw that this corrugated design worked really well. And you might wonder why I'm calling this corrugated. And you might think of corrugated cardboard. And if you look inside a piece of corrugated cardboard, you will see folds like this. You will see little triangles. And that's to make corrugated cardboard stronger, because really that cardboard is just made out of cardstock. It's not that hard to bend cardstock. But when it has those little folds and ridges in between 2 pieces of cardstock, it makes it much stronger. And so that's something that you could think about as we're going through this engineering type project, that all of the things you're learning in these experiments, there are things that could be used in real world design projects. One thing I've talked about before while doing that experiment was that we will use different materials when doing engineering projects, and that will depend, and we will use different designs depending on a number of different factors. And factors that are usually considered in engineering are cost as the first one, because you have to be able to afford it. There might be very, very strong materials for houses that we don't use, or more fireproof materials for houses that we don't use, because we value low cost, we value efficiency. That's something we might consider as well, is how efficient it is. We might consider the purpose of what we're designing something for. We might consider, am I designing this bridge for pennies, or am I designing it for people? How much weight is going to go on this bridge? Why am I building this bridge? Is it an overpass for a highway, or is it going over water? If it's going over water, are there boats going to be traveling under? Is it going to need to be split so that tall ships can get through? Because if you've looked at bridges, there are some bridges where they can raise the sides of the bridge so that a very tall ship can pass through a river. You might have noticed that I'm cleaning up my supplies, and that's because I'm going to move on to my next experiment, Ignite. And that next experiment is going to be on the mandala. I do not have my original mandala that I had made for this, so I am going to be showing you as I talk about it. So a mandala is a rotational symmetry pattern on a circle. And you've probably heard of symmetry in school a lot. You've probably thought about symmetry as when one shape overlaps another shape perfectly, or when you can have the exact mirror image of something, where theoretically that your face is symmetric. One side of your face is the mirror image of the other side. In real life, that's not actually true with faces. There are features of our faces that are slightly less than symmetric. We're not perfectly symmetrical, but we do have like 2 eyes and 2 ears, and it splits down the middle so that we have 1 eye on each side of our face and 1 ear on each side of our head. If you part your hair straight down the middle, your hair would be parted symmetrically. I do not have my hair parted symmetrically. And those are a couple of things you might be thinking about as you hear the words rotational symmetry. Right now, I am making a circle. This is because circular paper is very hard to find. So I am showing you how to make a circle. So I folded it in half, the page in half, and then I folded that half in half, and then I folded this sort of triangle shape, or, well, this top part is a triangle. This back part is kind of like a pentagon, or it is, well, as a quadrilateral, but kind of looks like it would be a pentagon. And then what you're going to do is you're going to cut a soft curve, not a very sharp one, because we don't want this to have like petals like a flower. We would just want it to be round like a circle, and you might trace with a pencil like a little line that you want to cut, a little curve. I kind of traced mine with my scissors, and I can see that because it indented into the paper a little bit. So now here is my circle that I'm going to demonstrate rotational symmetry with. A mandala is, and I cut it the wrong way, so now I have 2 half circles. Whoops. Okay. All right. Now I'll have to show you again the right way how to do it, because you see I cut it so that it was How did I do that? That is very interesting. That has never happened to me before while I was trying to cut out a circle out of a piece of paper. That is extremely interesting. Now, let's try that again and see if I can get it right this time. So, folding it in half, folding my half in half, how did I fold that before that it did that? I don't know. That is very interesting. I'm going to have to experiment with that. So now let's see. Will it work this time, or did I do it again somehow? Did I do that weird thing? No, I have no idea what I did. See, this is a sort of circle. If you look at it, it has little petals a little bit, and that's why I said that we want to cut a smooth curve rather than a sharp curve, because you can end up with that petaling a little bit. But it's good enough for this project. If I was really upset with it, I would figure out how I folded it, and I would fold it back up, and then I would trim this curve a little bit so it's a little bit smooth, and I would check and see if that looked better. And that is in fact just a little bit better. It's still petaled a little bit, but I'm happy with it. So we are going to talk about rotational symmetry. And as you've probably guessed from the word rotational, it has rotation in it. Now there are 360 degrees in a circle. So even if I had scribbles all over it, if I turned it 360 degrees, it would lay right on top of itself, right on top of that scribbled pattern. What we're doing with a mandala is we're making less than a 360 degree turn where the rotated pieces of our art are going to lie on top of each other. So we could do this in multiple ways. We could do it so that one half exactly reflects the other half. And that would be both like symmetry that you could fold and put right on top of each other. And it would be 180 degree symmetry that you could turn 180 degrees and top and bottom would be exactly overlapping. You could do 90 degree rotational symmetry where if I turn it 90 degrees, you have the same pictures on each 90 degree piece so that they would overlap. If I had another one exactly like it and I rotated a second one 90 degrees, I could still put it exactly over the top. So I'm going to do a 180 degree one because that sounds like fun to me. And because I love trees, I'm going to do that. So you're going to need, like I was using a piece of paper that you fold and cut into a circle shape. Hopefully this doesn't happen. I don't know how that even happened to me, so I don't know what to tell you if that happens to you. Except a very interesting party trick to share with people that you can accidentally cut 2 half circles instead of 1 whole circle. But I'm going to draw a tree with the markers that I have for this project. So I'm going to draw 2 trees that are going to exactly reflect each other. So this is the first couple of things that I've done. Don't worry, this isn't going to be super time consuming and it doesn't have to be perfect. This is just a demonstration of how it works. You could do it so that it is, when you turn it a third of a way, it's perfectly symmetric to itself, so it would overlap itself. You could do it, as I said, a 90 degree turn. You could do it so it, when you do an 1/8 of a turn or a 45 degree turn, it would be exactly symmetric. It would exactly overlay itself. There are lots of different things you could do for this. So I have my little tree base. Now I'm going to do all of the fluffy leaves. Like I said, this is really a fun project that you can do. It's a very simple project. So if you have little siblings in another room who are crowding around trying to watch, annoying you, you can always bring them in and they can try and do this too. They might not succeed, but it would be cool for them to try and do it, see how it goes. There are other ways for things to be symmetrical as well as rotational symmetry, and then that perfect cut in half symmetry. I'm trying to remember what that's called. I wonder if I have it written down somewhere. I have radial symmetry written down. Radial symmetry is the type of symmetry that you typically would find in invertebrates, particularly sea sponges, where is it sea sponges or sea anemones? It's one of those, where you can cut it down the center of its body in any way, and the halves would be exactly like each other. It doesn't matter where you do it, you would get two identical halves, like here, 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 whatever way you cut it. Whereas there are only so many, like if you go through the center of a square and cut the square into pieces going through the center of a square, it wouldn't necessarily be symmetric. Could probably go through the center of a square in a way where it would not create two triangles or two identical rectangles. So now I'm doing the other half of my tree. We like to talk about symmetry in math, but we also like to talk about it in science, because there are lots of ways that we see symmetry in nature. And we see a lack of symmetry in nature too. Like I was saying with our faces are not entirely symmetrical. Like you might have more freckles on one side of your face than you have on the other side of your face. You might have one eye that is slightly bigger than the other eye. So the halves of our body are not identical to each other. They're not perfectly symmetric. Oh, I thought of the way to describe radial symmetry for you. If you cut us in half like this, or put a mirror like this, you would get the other half of the body. But if you cut me like this, like right through the center of my head, my back does not match my front. And that is what rotational symmetry or radial symmetry does, where everything matches. No matter where you cut it down the center, if it goes through the center, it will match perfectly. This is not radial symmetry. Like I said, this is rotational symmetry. So, magic time. Flip it 180 degrees. It's exactly the same. Magic. And that is a mandala. You can do as much of this or as little of this as you want. You can do as much art or as little art as you want on yours. I'm going to move to my next project because I have a lot of fun stuff prepped for tonight, and I want it to be a lot more things than just that one thing. And I know that not everyone's favorite pastime is to do art. So this is the next one that we have, which is making a Benham's disc. And let me look through. That's where that is. So now we are going to make what is called a Benham's disc. And you may be going, well, what is that? And why are we making it? And to that I answer, it is an optical illusion. Optical illusions happen when our brain sees something that isn't exactly what is going on. Like if you've ever seen one of those pieces of art where there's a lot of squiggles painted, and if you look at it, it looks like the art is moving. That is an optical illusion, because we know that the art isn't moving, but to our eyes, those wiggles appear to be moving. Or when you look at those optical illusions where it looks like someone is going to fall into the floor through a particular rug that looks like it makes it look like there's a hole in the floor. That is an optical illusion as well. It's our brains seeing something that isn't really there. Our brains are misinterpreting the information that we have. So you will have gotten a little Benham's disc. Trying to think of the word for it. A little template. There it is. And template that we're going to be working with is made in a special way. It's a pattern of white and black rings on a circle. And the interesting thing about a Benham's disc is this makes you see colors when it spins. So we are basically making a top. We're going to take this piece of paper and we're going to glue it down on a piece of cardboard. And again, you might be asking, why are you gluing it down before you cut it out? And the answer to that is because it's really hard to freehand a circle on cardboard. So I want this to exactly overlap. So I am just putting it down on my piece of cardboard, and then I'm going to cut out the circle. And then I'm going to take a toothpick and stick the toothpick through it, and that toothpick is going to come out the other side, and then we're going to use that toothpick as a top. So fittingly, for the fact that Benham's discs are usually displayed as tops, the Benham's disc optical illusion was discovered by a toy maker who found that particular patterns of black and white as a ring on pieces, or as a ring like this, would make people see colors when it spun at a certain speed. So you're going to try and put this through the center of a piece of cardboard, and then you're going to spin it. So you're going to put your toothpick through your cardboard, break off the top, and then you're going to spin it. And you're not going to be able to see colors very easily with me just spinning it with my fingers. And maybe you won't see it on your top either, because toothpick tops don't always work super well. But when this gets spinning fast enough, you will see multiple colors. Most people do. About 30% of people don't see multiple colors when they're spinning theirs. And if you don't see your colors on yours, you might try to search it up online. And there are videos of people with Benham's discs where they will show the colors that you would see. And you might see red or green or blue instead of white and black when this spins quickly enough. The ideal speed is pretty quick, so who can say if I will be able to get this to do it? Yeah, no, I don't think it's going to, but there is that. You can try, and I will explain how the Benham's disc optical illusion works. Scientists have a couple of theories as to why, and they're to do with complicated organs in our eyes. And, well, not organs, but structures in our eyes that are called photoreceptors. Photoreceptors receive light and they process that light, and that is how our brains see, is that those photoreceptors send signals to your nerves that process the light you see as vision. You may have noticed that if you get shut up in a dark room, you can't see nearly as well. This is because we see using light. Our brains interpret light as vision. And the things that we see around us, the things that the light bounces off of, we see as vision. That was a very poor description, I apologize, but you can look up more about photoreceptors if you'd like to know more. Then we have rods and cones, which are two types of photoreceptors. So those are structures in our eyes that respond to light. Those are rods. And then there are cones, which are photoreceptors that process color. So rods primarily deal with light, and cones primarily deal with color. And it is these two types of photoreceptors that create the Benham's disc optical illusion, where we see colors instead of white and black on this rotating disc. So basically the theory is that when we have those cones interacting, because different cones interact and react to different colors. So black and white would not be responded to by the same exact cones. So while this is turning really quickly, our brains might lose track of which cones to keep on. The cones in our eyes might get tired, and they might shut off in certain patterns, which create the illusion of color because some cones aren't processing when we're seeing the black or we're seeing the white. And that is how we see the colors. And that is the theory that they have. They aren't sure whether that's correct, but that is one of the theories about Benham's discs. And that would be another great thing to research by yourself. Now, I wanted to show you one last cool one that revolves around something I've been obsessed with since I was very young. And that is astronomy and the zodiac. And we're still going to be using paper, and we're still going to be using markers. So if you have those and a pair of scissors, you're good. I'm going to grab my template of my stars that I accidentally left on my printer, and I will be right back for you. So we have that here. All of the zodiac constellations. The constellations of the zodiac, a lot of you probably know them if your parents maybe told you that you were a Cancer or a Gemini, or like me, a Sagittarius. And what that means is that those constellations were used a long time ago, before we had things like calendars. Those things were used to keep track of months, because as the Earth rotates around the sun and as we move through space, we see different constellations in the sky, and the sun appears to be inside of different constellations because those constellations are way far away and the sun is closer up. So as we move around the sun seems to be blocking certain constellations. The sun seems to be inside of them because we're maybe over here and the sun is here. And so even though the sun is right here and the sun is not moving inside of those constellations, it appears to be. So those constellations that the sun does appear to be inside of are called the zodiac constellations. They were come up with primarily by the Greeks and Romans, so they're not a universal experience. They are primarily from the Greeks and Romans. We have constellations from a bunch of different colors because constellations were a way that the people a long time ago would keep track of seasons, of directions in the night sky. And they had different cultures, so they saw different things. When they looked for pictures and patterns, they saw different pictures and patterns because they had a different interpretation of how the world worked. The zodiac constellations were important because Rome was important in Europe, because Rome took control of the world historically. And that's why those became such a memorable set of constellations, not because they were better or more important or the correct set of constellations, but because the people that had control over the world at the time, a long time ago, and for a long time had influence over the world, saw the world in this way. And so those constellations became remembered. But I wanted to show you what the constellations of the zodiac look like. So I cut a piece of paper in half, and now I'm going to start drawing the zodiac constellations. I think this shows them in order. I might be wrong, but I think they're shown in order. Hopefully. If they're not, I apologize very strongly. And those of you who know the zodiac better than I do will be at home going, why are you drawing them in that order? But I wanted to show you the zodiac constellations, so you can try to draw them along with me. So I will show you each time that I draw one, and I'm starting with Aries. Each of these constellations has a story that goes along with it, because part of the reason that the Greeks and Romans thought that these were the constellations in the sky were because they had stories as part of their mythologies. Like if you've heard of Orion the Hunter, it's a very easy constellation to spot, and that constellation is very connected to the Greek myth about Orion the Hunter. So this is my messy sketch of the constellation Aries. So you can see a star here, a brighter star here, another one here, 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 here. And you can draw that if you would like. I'll give you another second to look at it. And like I said, this would be another great thing to search up on the internet. And you might be going, well, it's very nice that those people way back when loved to look at the sky and see pictures, but is that really relevant anymore? Because we have things like calendars, and we know that constellations are subjective, that those stars are not actually forming pictures in the sky. They are just in the sky, very far away from each other, in space, suspended in space by gravity and by other forces. And they're just moving through space. And we know that none of these stars are actually forming these constellations. Why is it important that we know these constellations? This one is Taurus. And the reason that these constellations are so interesting is because this is how they used to tell time. Before they had calendars, well, they still had calendars then, but when they were still figuring out how calendars worked, the way they figured that out was the movement of the planet through space. That was how they figured out time, was how they saw seasons change, how they saw things on Earth change, and how they saw these constellations move in the sky. Next, I'm drawing Gemini. We figured out our set of constellations our count. Okay, I apologize. Sorry about that. My internet just cut out. I don't know how it's been for everyone at home, but my internet has been all over the place. So basically what I was doing was finishing up my zodiac constellation chart. And while I'm sure that everyone at home has already lost interest, because that was like 2 or 3 or 5 minutes of total silence, I just wanted to encourage all of you to take the opportunity to learn more about science when you have a chance, and to do more awesome engineering activities and math activities. And thank you so much for coming to this event and for being such great listeners and learners for me. Thank you so much. Thank you, DoSpace.